All right, folks, here we are on the very last section of Chapter 2 on nonparametric methods. So what he's going to do is he's going to describe what he means by nonparametric methods, and then we'll discuss three of them. The very first one that we're going to discuss in this, what I think will be a short video, is the histogram method. And then the next two sections we'll discuss slightly more sophisticated methods called the kernel density estimators and nearest neighbors. So let's get into it. Okay, so he says, throughout this chapter, we have focused on the use of probability distributions having specific functional forms, governed by a small number of parameters whose values are to be determined from a data set. So, an example of this was when we were trying to describe a data set, let's say using a Gaussian distribution. And so we have two parameters there. We have the mean and the variance, and they will then determine, which member of that family we're going to use for the data. But they all have kind of the same, exponential so-and-so form. And this is called the parametric approach. Oops. Again, you can guess why, right? Because we're just fitting the parameters of stuff. We've picked the family and we're just fitting its parameters. So the parametric approach to density modeling. So now, obviously, an approach and a big limitation of this is that the chosen density might be a poor model of the distribution. And so you're going to get poor predictive performance. So a good example of this he gives here is that if the data is multimodal, so it has kind of multiple peaks, and then you choose a Gaussian, well, you're not going to be able to fit it very well. So what are we going to do about that? If we don't know, what distribution to use, or maybe we want to kind of let the data pick the distribution somehow. In this final section, we consider some non-parametric approaches to density estimation that make few assumptions about the form of the distribution. So that's good. And here we shall focus mainly on simple frequentist methods. So we're not going to see things like priors and posteriors. We're just going to we're just going to kind of estimate these probabilities in a maybe a heuristic way. The reader should be aware, however, that non-parametric Bayesian methods are attracting increasing interest. So this book was written in 2006, where this stuff, I guess, was coming up. When I did my first postdoc around 2012, it was still a very big topic, and I'm sure there are still people working on this. And this is actually quite cool because it allows you to use Bayesian techniques and kind of use distributions that kind of naturally expand to accommodate the data. They get more and more complex as your data gets, as you get more and more data. So it's a very cool topic if you're interested and you want to look into it. There are some references here that you can pursue with. Okay, so we're going to be working on the simple frequentist methods. Okay. So let's start with a discussion of histogram methods. So let me highlight that. That's what we're going to be talking about in this particular section, which we have already encountered in the context of marginal and conditional distributions. You've probably seen them yourself lots of times. Here we explore the properties of histogram in more detail, focusing on the case of a single continuous variable. Yeah, because it's going to be, you'll get the point already in one dimension. Okay, so how does histograms work? Well, we simply partition X into distinct bins of width delta I, and then count the number ni of observations of X falling into bin I. So actually, it's just easier. Let's just look at, I'm sure you've seen this a million times, but let's just look at, what this can look like. So here he's got kind of an example where the data is being generated from these, distributions. So I think the actual data points aren't shown, but they were sampled from this distribution, I believe. Yeah, so in which data set of 50 data points generated from the distribution shown by the green curve. So you have kind of a bump of data around here and another bump of data around there. And then the idea is that you're going to bin up this domain into, these little bins, and then just count how many of your points fell into each one of those bins. And now here, all of these bin sizes are the same, but in general, they don't have to be. So you can use kind of different bin sizes. So we're going to be essentially trying to model the distribution as with these regions of constant probability. And the question is, how do we assign those probabilities? Okay. So he says, they simply partition X into distinct bins of width delta I. So the index I means that those bin sizes can change. They don't have to be constant. And then count the number ni of observations of X falling into bin I. Okay, so now he says, now how are we going to turn this into a probability? So how are we going to get those, the heights of those bins? Well, we simply divide by the total number of observations and by the width delta I of the bins to obtain probability values for each bin. Okay, so here's the expression for it. Now, it took me a second to kind of understand where that expression comes from. And it's actually easier, I think, to write it. I think it's more, instead of writing it in terms of that, to write it as, let's just zoom in here a bit. Okay, good. So we'll just write it as Pi delta I is equal to ni over n, right? So that's expressing the same thing. And now why is this more, perhaps more intuitive? Well, you can imagine that, let's say you've got your bin here. I'll just call this region I, right? And now you want to we want to figure out how to assign the probability to it, right? And we found that there's ni of the points have fallen inside this bin of a total fraction of n. So the probability, the total probability in that interval is, let's say we're going to go p of x dx, and let's just call this, I'm just going to call this region I, right? And the total probability in there is, within our histogram, is actually just going to be some constant value times the length of that interval. So instead of having this, we actually have an integral in here, but it's actually just a simple one because p of x is constant and d of x is just the interval. So the total probability that we have in this interval is, in general, for whatever distribution, is given by this expression. But for a histogram, it really simplifies because we're going to assign a fixed probability over the entire region, and the width is delta I. So this d of x, so this is that, and this is that. So I think this expression is a bit more intuitive than this one, at least for me, although they're expressing the same thing. And then also from once you get that, where that intuition comes from, then this statement, that from which it is easily seen that the integral of p of x dx is 1, well, that's easily the case because we derived it from this expression where we know that if you integrate it over the whole interval, it's going to integrate to 1. So yeah, so I think it's maybe a more intuitive way of thinking about it. Okay, so now this gives a model for the density px that is constant over the width of each bin, right? So we have this probability distribution. We don't know what these p's are, and we just find them by integrating over the bin and getting comparing that value to our actual number of observations. That's it. Yeah, and often the bins are chosen to have the same width, but again, that's not necessary. Okay, so and here's kind of an example. We already talked about it. So again, he's got data. He's always sampled it from this distribution, but now he's used different bin sizes to show the effective bin sizes. And you can see that there's kind of an optimal bin size. Like, I don't know, maybe this one kind of seems to capture it a bit more. But again, that could be, in this particular case, I think it's because the widths of these two modes are about the same. You can imagine if one mode was really thin and another mode was really wide, then you might want to, you might not find the best fixed width. You might want to, adjust the bin widths or whatever. But it's just one of those games you have to play. So yeah, it just kind of talks about there's a good one, there's a bad one, but the best results are obtained for some intermediate value of delta. And it says also, the histogram models are dependent on where you pick the edges, but in general, I think, and in my experience, it doesn't matter too much as long as you've got enough bins. Oh yeah, and so one heuristic, and I don't know where it comes from, though I'm sure there's kind of a simple explanation for it. Number of bins should be approximately equal to the square root of the number of data points. So yeah, I've had good good experience with using that heuristic, and in the 1 or 2 dimensions where this stuff works. Okay, in principle, a histogram density model is also dependent. Yeah, so we just talked about that. Okay, so now, yeah, so it's got this cool property that note that the histogram method has a property, unlike the methods that we're going to discuss, that once the histogram has been computed, the data itself can be discarded, right? So once we've got those PIs and those delta I's, we don't need the data anymore. We've got our estimate. It's going to be this blue thing, and we can now work with it, do whatever we want with it. And so this can be advantageous if the data set is large. Also, the histogram approach is easily applied if the data points are arriving sequentially, right? Because you just, you put each data point in, and you just perturb some of those PIs basically in a simple way. In practice, the histogram technique can be useful for obtaining a quick visualization of the data in 1 or 2 dimensions, right? It's unsuited to most density estimation applications. So one obvious problem is that the estimated density has discontinuities due to the bin edges rather than any property of the underlying distribution. Okay, but I think the really big one is the scaling with dimensionality. So, if we divide each variable in a d-dimensional space into m bins, then, the total number of bins, so there's m in each direction, so it's going to be m to the d. And you often, it's very common to be working with 10, 100, even 1,000 dimensional data. So what's going to end up happening there is that you don't have enough data to essentially fill most of those points. So this exponential scaling with d is an example of the curse of dimensionality. So in a space of high dimensions, the quantity of data needed to provide meaningful estimates of local probability density would be prohibitive. So yeah, if you're just trying to build there's just too many points given the for any reasonable number of dimensions, you'll need way too many points to get even a single data point in each one of the boxes, and so you're going to get very kind of noisy estimates basically. So the histogram approach to density estimation does, however, teach us 2 important lessons. So first, to estimate the probability density at a particular location, we should consider the data points that lie within some local neighborhood of that point. Okay, seems pretty obvious. Now, the locality requires we have some form of distance. Fair enough. We've been using Euclidean distance. You can use other distances. For histograms, this neighborhood property was defined by the bins, and there's a natural smoothing parameter describing the spatial extent. Okay, that's all pretty obvious. Okay, now second, the value of the smoothing parameter should be neither too large nor too small in order to obtain good results. So this is this is exactly kind of a model complexity situation, right? If your bins are too small, it's almost like you're using kind of too complex a model to fit the data. If they're too large, it's almost like your model is too simple. So you have to find a good so you have to kind of, just exactly the same way as we discussed before in chapter 1 with picking like the order of the polynomials, you have to find, have some mechanism of finding a kind of a good intermediate value, neither too large nor too small. Okay, so I think that's on with these insights. We now turn to discussion of 2 widely used non-parametric techniques for density estimation. So kernel estimators and nearest neighbors, which have better scaling with dimensionality than the simple histogram model, although he doesn't really go into this, so he's just going to tell us what they are. So we will start with kernel density estimators next. So hopefully you enjoyed this video, you learned something, and you will join me in the next one. Thank you.